All right, this is Mr. Jern, and I'm going to talk to you today about work, energy, and power. So, work is symbolized with a capital W. It doesn't need to be italicized, it's just kind of how it is here. And work is just the energy that's transferred when a force is applied to an object through a distance. Okay, so the equation for that can be written like this: work is equal to force times the distance. And all this little symbol means is parallel. So in other words, like, it's the force, like if you're pushing on something or pulling on something, you only count the force that's actually parallel to the direction that the object is moving. So if you're pushing something at an angle, you would only count the part of the force that's actually parallel to the distance. Now we're going to keep things simple for a little while and not really worry about angles too much just yet. You'll know when they're there, but this is the simple formula, which again, you won't have to memorize. It's all on your formula sheet. All right. The SI, or the international System International. See, I try to get all fancy. It's an international system, metric, if you will, sometimes. The SI unit of work or energy is the joule. The symbol is the J. So 1 J is equal to 1 Newton meter, because the SI unit of force is newtons and the SI unit of distance is meters. So when you multiply them together, that's the unit of energy. Now, so we have an example here. Excuse me for coughing. That was very rude of me. A student lifts a 50-pound ball 4 feet in 5 seconds. How many joules of work did the student complete? Well, we start with our equation. Work is force times distance. We just multiply those two together. So the force is 50 pounds, the distance is 4 feet, and we get the amount of work is 200 foot-pounds. Okay, now that's valid, especially in engineering maybe, but it's not in SI. So can we convert it to metric, basically? And the answer is yes. So in metric, first we have to convert our numbers to the SI units. All right, so we do that by saying, all right, 50 pounds. Well, there's 1 Newton for every 0.225 pounds. And so if we do the calculation there, then 50 pounds is 225 or 222.5 Newtons. 4 feet, well, there's 1 meter for every 3.28 feet. So if you ever notice that a meter stick and a yardstick are about the same distance length, then this is why. Then 4 feet is about 1.22 meters. And so we take our equation of work is force times distance, and we get the SI unit of work here is 271 joules. So that's work. That's the calculation. And I said in the first slide that that it is also the unit of energy. Where'd it go? There we go. It's also the unit of energy, that joule. So what is energy? So let's talk about energy really quick. Energy, it's not a person, place, or thing. It does not matter at all. It's nothing you can touch. It is more of an idea, but it is definitely something. Simply put, energy is the ability to do work. Okay, so however much energy you use, that's how much work you can do. However much work you did, that's how much energy it required. That's why work and energy are the same. We have a lot of different types of energy that we deal with: light energy, heat energy, mechanical energy, chemical. All these things, electrical, are all different types of energy that can be used to exert a force for a distance, okay, to do work. So we have some examples here. We got a roller coaster, NASA solar sail, a fuel cell. All these things involve capturing or using energy. So the two basic forms of energy is going to be potential and kinetic energy. You probably learned that a long time ago. Potential energy just means it's stored energy. What does it have the potential to do, or the ability possibly to do? Usually we talk about it, especially if you took physics, in terms of gravitational potential energy. When you hold a ball up, it gains potential energy. The more energy it gains, the higher up it gets, and the more energy that it can use to get faster and faster as it falls. Not usually, but potential energy can be further and slightly more confusingly defined as it has to do with the capacity to do work by virtue of position or configuration. And all that means is exactly what I just said. Like this helicopter in this picture, the higher up it is, well, it's got a, what's the position compared to the ground? Well, if the higher up it is, the more energy it has. What else other kinds of energy? There's also elastic energy. Okay, talking about the position or configuration. The more you stretch a rubber band, well, the more energy it took to stretch it and the more energy is stored there. You have chemical energy, talking about how different molecules are arranged and how they're arranged, the position, it kind of informs how much energy they have. You have thermal or heat energy. What are the molecules doing? Where are they at or what are they doing? And it's all about, here, keep it simple. Potential energy is stored energy. Okay, how is it stored? It's stored somewhere in some way. And the way it is stored speaks to how much energy it has. What is it used for? Typically, kinetic energy. Okay, it's the ability to do work, the energy of motion. Okay, there's all sorts of kinetic energy, different things move. We could talk about big things moving, like a ball falling, like you might talk about in a physics class. We could talk about chemical energy, where the molecules are moving type of thing. You could talk about, it's kinetic energy still. It's all kinetic energy. You could talk about thermal or heat energy, where you talk about how the atoms jiggle, and the more those atoms jiggle, the more heat they have. It's all about that motion. It's all about that motion. So let's talk about some energy transformation. We have some examples here. Basically, very common one is changing pizza into kinetic energy. You eat food, you eat chemicals, and you change that into movement, motion, kinetic energy. You gather, plants will gather, in solar power, solar cells will gather energy, radiant energy from the sun. And in terms of plants, they change it into chemical energy. You can see a tiny little picture of that's a plant that doctor is holding, that scientist is holding. So they change it into chemicals. Plants store the energy, the radiant energy of the sun, in some sort of chemical form. In other words, like the chemicals that it's made out of. We change electrical energy maybe into thermal energy. If you use a electric oven or stove or something like that, you could change energy into heat. If your cell phone's getting warm, your computer's getting warm, that's an example of changing electrical energy into heat, thermal energy. We talked a while ago about the different types of renewable energy sources. So just to kind of recap, biomass is the energy stored in plants. Hydropower is the energy stored in, again, the configuration of the water. It's high up on one side of the dam, low on the other. Biomass, it has to do with the energy, how that molecules are arranged. Geothermal, that's the energy of heat deep in the earth. So the molecules that are hot are farther away and they have just more thermal energy compared to like their surroundings. And so we can use that difference to, just like we use the difference in height of water to extract that energy. You could use the difference in temperature to extract geothermal energy. Wind has to do with what's wind? Wind is air that's moving from an area of high pressure to an area of low pressure. That's renewable energy source, and we use that difference once again. Solar, well, again, it's about the difference. There's radiant energy coming from the sun, and it is a slightly different type of that is definitely radiation type energy, radiant energy, as I said earlier. So all those are renewable, meaning that we could get more of them. We also have our non-renewable energy sources: coal, natural gas, petroleum, uranium. All those are non-renewable. We've talked about those before. So a law: conservation of energy. Energy cannot be created or destroyed, but it can be changed from one form to another. Okay. When we talk about energy being lost to heat, well, that happens a lot. Okay. In fact, it happens all the time. There's no getting around it. When you input energy and it changes to output energy, some of that energy is usually heat energy. Okay. When you change your chemical energy to kinetic energy when you're running around, there's heat. You get warm. All right. Your laptop, your phone, your computer gets warm. That's not a desired effect usually. And so that's why we say energy is lost to heat. The energy is still there because it just got changed into a form that we don't necessarily want. So we say it's lost. We don't want that energy to be lost to heat. We don't want it to change to heat. And so it's lost, never to be captured again by us, usually. Stove or something, maybe it is meant to be too, but even then. So some examples of conversion. We talked about transformation of energy. So these are some very common things in terms of fossil fuels. We change chemical energy, whatever that may be, gasoline, right? Then it burns, we turn it into heat in our combustion engines. That causes some sort of mechanical energy in the engine. And there's different components of cars that will not only cause your car to start to move, but it also powers the electrical components of the car. Okay, the alternator does that typically. Solar cells will take sunlight and change it directly into electrical energy. There's wind turbines that take the kinetic energy of the wind and change that into mechanical energy of the turbines spinning, which then generates electrical energy. Hydroelectric, the gravitational energy, potential energy of the water that's higher up. Well, that can be changed into mechanical energy as the turbines spin again, and that generates electricity, again, similar to the wind turbines. Nuclear energy, we got these big old nuclei of these huge atoms, very unstable, and we break them apart, and that generates heat. So some energy is lost, but we try to capture as much as we can. That boils water and it turns turbines. The steam turns, it causes turbines to spin. And very similar to the hydroelectric and the wind turbine, we get electrical energy from those spinning turbines. When we talk about a car specifically, we got this chemical energy, gasoline, and we get mechanical energy out of it, which we want. Okay, that's the output that's desired. And we also get a lot of heat, which is not necessarily desired except for maybe in the winter. But even then, there's better ways to do that. Okay, so that's something to keep in mind. We get two types of energy. We could also change that mechanical into some electrical in the car, which we do. So speaking of heat loss, we got to talk about efficiency. And this is the meat and potatoes of where we're going with this, because we're going to do an activity very shortly dealing with efficiency. The efficiency, we got another Greek letter here. This is an eta, or an eta, I say. It's just a Greek letter, and all that means efficiency is the percentage of the input energy that's transformed into the output energy that we want. Okay, so what is the output energy that we desire? Okay, in terms of a car, it would be the mechanical energy divided by how much energy is put into the car. Okay, now it's usually written as a percentage, so we're going to have to multiply that by 100. You might be surprised to know that the amount of energy that a car uses with gasoline, now it depends, of course, on fuel efficiency and all that. That's what that's all about. We get roughly 30% efficiency. Most of the energy is lost to heat from burning fossil fuels. Most of it. Okay, and it's not just lost at the burning. There's also a lot of friction involved. There's all sorts of places for energy to be lost as heat. So bottom line is, though, this efficiency is how much energy you're getting out of it versus how much energy you're getting into it times 100. Okay, now this next slide is a little bit possibly out of date by now, but it gives you a general gist of where we're at. So this is the current, as of a few years ago, energy concerns. Well, we got consumption. Here's the consumption. Here's the types of energy that we use as of a few years ago. You go to this website, probably get some more updated results. But some concerns are just how much is consumed. What are we doing about the pollution based on that? What about depletion? We're running out of some of our sources. Dependency. Are we dependent on resources that we can't get or are costing us maybe national security or something? And the costs are going up for fossil fuels. Cost is coming down for renewables like solar and wind. So what roles do you suppose engineers have in energy? Are we going to be using more energy as time goes on or less? Probably a lot more. I mean, if trends continue, exponentially more. Well, engineers get to solve these problems, okay? And not decide, but work toward better solutions about how to do all that. and solve those problems. Okay, so switching gears slightly, let's talk power. Power is the rate at which energy is used to do work. Okay, whenever we talk about a rate of something, it's going to be something divided by time, over time. How much time was used for this? So power is either the energy spent per time or the work done per time. It's the same thing. Well, usually the same thing depending on what you're looking at. Okay, you could talk about the energy that you put into something. You could talk about the work that's done by something. It depends on the situation, but it's basically the energy or work performed per time, usually in seconds. The SI unit for this, for power, is watts, which you've probably heard of once or twice in your life. And a watt is 1 joule per second. In other words, a watt is something that's either using or expending 1 joule of energy per second. That's a watt, and that is a unit of power. So joule is the unit of work or energy. Watt is how much of that energy or work is used per second. Okay, so a old-fashioned 60-watt light bulb uses 60 joules of energy per second. Okay, you look at the wattage of different appliances, and you could tell how much energy is being used per second. That's what that's getting at. Okay, so talk about types of power. You have electrical power. You could input electrical power. It's how much electrical energy is done to you to do work. Again, how much per second. We talk about mechanical power, linear power. Think about like well, anything that involves like a piston usually, or anything like that. Using mechanical energy to do work. Rotary power, something spinning. So boy, what's an example? Like a gear maybe could be considered using rotary power or employing rotary power. There's also fluid power, which we're going to get into later. Hydraulics or pneumatics are all about using fluid power. Again, how much energy is expended or used, or how much work is done per second, per time. So for an example, let's look at that ball from a while ago. So the student lifts 50 pounds of ball, a 50-pound ball 4 feet, and you might have been wondering what this was about, the 5 seconds. Well, how many watts of power did the student use to lift the ball? And now it's also going to answer, why did we have to convert it to SI? I thought this was engineering, or Americans here. We use engineering terms, not science terms. But this is why, because we're going to talk about in terms of watts. Now there is horsepower and there's other units of power, so I'm just kind of messing with you a little bit on that one. We got the work as 271 joules of work. We got that by calculating that out. And so for power, we're going to take those joules divided by the 5 seconds, and we get 54.3 joule seconds, which is 54.3 watts. That's essentially it. All right, so that's, yeah, if you have any questions, just please let me know. You guys have a wonderful afternoon and wonderful day. Bye.